Welcome friends. Today we are going to continue our session in which we started differentiation by first principle. So we shall continue. We will try to derive a few more standard results for differentiation. So differentiation by first principle. So in previous lecture we have derived the differentiation of some standard functions. So you can see, so this is the function y equal to f of x is a function and its derivative is dy over dx, or we can write f dash of x. Both have same meaning. Initially we took an algebraic function which is x raised to n, and we found that the differentiation of x raised to n by first principle as n times x raised to n minus 1. Okay, here n is a number, n is a constant term while x is a variable. We also discussed about a constant function. If you have a constant, some constant c, so derivative of the constant would be 0. We have also discussed about differentiation of trigonometric function. If the function is sine of x, the derivative or differentiation of sine of x is going to be cos of x. We also discussed derivative of cosine of x as minus sine of x. If you take secant of x, its derivative is going to be secant of x times tangent of x. And if you take cosecant of x, it will be minus cosecant of x cotangent of x, that is cot of x. We can also see that derivative of tangent of x would be secant square x, and derivative of cotangent of x is minus cosecant square. We also discussed exponential functions like a raised to x, where a is constant and x is a variable. So the differentiation of a raised to x is a raised to x natural log of a. If you take e raised to x, then you will get e raised to x. So derivative of e raised to x is e raised to x only, right? Today's session we would like to take few more functions and try to understand what is going to be the derivative of that. So first of all, we shall be taking logarithmic function. So what is going to be the derivative of logarithmic functions? So we will try to see how to find derivative of logarithmic function by using first principle. So as example, we can take y equal to f of x, and that is equal to log of x. So basically it is a natural log of x. So by first principle, as we know, by definition or by first principle, derivative is given as limit delta x tends to 0 f of x plus delta x. Delta x is a small increment in the x divided by increment in the x, which is the definition of differentiation. So since f of x is log of x, therefore f of x plus delta x log of x plus delta x. So we can substitute this value of f of x and f of x plus delta x in this particular expression, and we can solve the limits and find the value of derivative. So substituting equation 1, therefore derivatives dy over dx of function would be limit delta x tends to 0 divided by delta x. So we can substitute the corresponding values. So limit delta x tends to 0. Since natural log of a minus natural log of b is nothing but log a divided by b. So if you use this result, what you shall be getting, I'll write down here itself so that, so limit delta x tends to 0 log. So this can be further written as limit 1 over delta x log of. Now if you look at this, you will divide x by x, so it will become 1 delta x by x. So you will be getting like this, 1 plus delta x over x. So we can continue from there itself. So therefore you can write down dy over dx equals limit delta x tends to 0, and then we have this 1 over delta x can be taken into the exponential form. So you can take this whole thing into the exponential. This may go in the exponential here. So what you will get is interesting. Log of, let me write down, 1 plus delta x by x whole raised to 1 over delta x. Find it. We have relationship like this. Since a times log b is log b raised to a. So now you have to remember a very important limit. That limit is something like, you must be knowing that limit x tends to 0. It is standard form of a limit. 1 plus x raised to 1 over x. This value is e. This is a standard limit. So you have to be very careful here that whatever variable you have here, the same variable must be here, and then its reciprocal must be here. So if it is x, you should have x here, and you should have 1 upon x over here. So we can transform this whole equation, this whole limits in the similar form. So let me continue from the next page. So I'm writing it again. So we have dy over dx equals limit delta x tends to 0. Then we have log 1 plus delta x by x, and that raised to 1 over delta x. This is what we have here. Now, by the rule, if we have delta x here, we should have delta x here. But if you look at here, we are getting delta x by x. So somehow, we have to adjust it such that the same variable must be here. At all points, you should have same variable. So I'm going to do some small adjustment. So what I'll be doing is very interesting. We can write down that as delta x tends to 0. So if I divide it by x, the value will not change. Therefore, delta x by x will also tends to 0. We are trying to develop this form, that is limit x tends to 0, 1 plus x raised to 1 by x. We wanted to create in this form. So whatever variable we have here, the same variable must be here. But if you look at this, our situation, here we have delta x by x. So we should have here also delta x by x. So to introduce delta x by x over here, I am simply dividing delta x by x. So as delta x tends to 0, delta x by x will also change to 0. So then I'll get a new limit. So instead of writing delta x tends to 0, I can write delta x by x tends to 0. That is one thing I can do. Second thing is, whatever is here, delta x, so I should have reciprocal of that over here in the index. So that also creates, so I'll simplify that. Now mind it, one more thing is very important. The limit is only applicable to the variable. So this log part can be taken outside, can be taken out of the limits. So what I will do is dy over dx. So I'll write down log outside because, and then I'll write down limit. It is now new limit I'm going to apply, delta x by x tends to 0, and then inside we have 1 plus, so 1 plus delta x by, now I'm going to do small modification here. I'm going to divide and multiply by x here. So it is going to be x by delta x, just to create this particular form, and then into 1 over x. In the index I am doing division and multiplication by x. Okay, so if you look at it now, it is quite simplified. So this can be written as, log will be as it is, and I'm going to write down the remaining part here, that is limit delta x by x tends to 0, inside 1 plus raised to x by delta x raised to 1 by x. So that raised to 1 by x part I've just kept outside the whole bracket, so that the situation becomes quite predictable. Okay, So now if you look at this particular term, so it is in somewhat this form. If you call this as some variable x, so x tends to 0, 1 plus x raised to 1 over x. So this value would be simply e. Okay. So therefore we will be getting dy over dx equal to log will be as it is, log this value we got as g now, okay, whole raised to 1 over x. Now as we did earlier, this part can be taken here also as a coefficient, so you will be getting 1 over x log of e, and we know that natural log of e is 1, so therefore the final answer is going to be equal to 1 over x. Okay, so what is the final conclusion? The final conclusion is like this: if y equal to f of x equal to logarithmic function of x, then dy by dx, that is derivative, or f dash of x is going to be 1 by x. Okay, so this is we got for standard function as log. So for logarithmic function, derivative of log of x is 1 over x. So we have completed almost trigonometric functions, algebraic function, exponential and logarithmic function. Now remaining is the inverse function. So let me take example of inverse function. So we will discuss how to find derivatives of inverse trigonometric functions. So there are different ways by which you can do this, but I would like to stick to simplest method. What I shall do is, let's begin with the first one. So I am going to start with the sine inverse of x. So we have y equals f of x, that is sine inverse of x. Okay, before starting this, I just want to tell you very important result. So what is that result? Please remember, this is an important result. It is dy over dx is same as 1 divided by dx over dy. Okay, so if you want to differentiate y with respect to x, you can differentiate x with respect to y and then take reciprocal of that. So this we shall be proving this later on, that dy over dx equal to 1 by dx over dy. So I am going to use this result. So let's see how we can proceed. So I am going to say that therefore y equals sine inverse of x. Then you can bring this sine inverse this side, and this will become therefore sine of y equals x, or we can say x equals sine of y. So if you look at this, we can differentiate this with respect to y. Now we have already discussed what is the derivatives of sine. So derivative of sine is cos. Very simple. So the same way I will differentiate this. Let me call this as equation number, this I am going to call as equation number 1. Differentiating with respect to y. Therefore you will get derivative of x with respect to y. Derivative of sine is what? Cos. So we have already done it. Cos y. So by this rule, if you look at this, by this rule, therefore dy over dx would be 1 divided by dx over dy. So that will be equal to 1 upon cos y. Now the question is, what is the value of cos y? So we know that there is a important identity, that sin square y plus cos square y equals 1. So therefore cos square y must be equal to 1 minus sin square y, and hence cos y would be equal to under root of 1 minus sin square y. This is already known to us. Okay, so this is nothing but 1 divided by 1 minus sin square y. If you know what is sin y is x. So sin square y would be what? X square. Therefore derivatives would be 1 divided by under root of 1 minus x square. This is the result we got. So it means if y is sin inverse of x, its derivative is 1 divided by 1 minus x square. Similarly, you can also find out y equals f of x equals cos inverse of x. So derivative of cos inverse of x would be, if you continue with the same method, you will end up getting minus 1 divided by 1 minus x square. Okay. So you can similarly you can approach, you can derive derivative of cos inverse of x. Let's take another one, that is tan inverse of x. Let's see how we can approach tan inverse of x. So we have y equals f of x tan inverse of x. So that will give you tan y equals x, right? Same procedure we are following. Therefore x equals tan y. So differentiating, now we will differentiate with respect to y. So differentiating with respect to y, so dx over dy. So you can see here we already got the results. Derivative of tan x is secant square x. Okay, so let me put that here. So derivative of tan y would be secant square y. Okay, so therefore by the result, by this rule, that is dy over dx equals 1 divided by dx over dy. So by using same result, you can therefore dy over dx, so that is 1 upon sec square y. We have 1 plus tan square y. We have 1 plus tan square y equal to sec square y. So instead of sec square y, we can substitute this value. So 1 upon 1 plus tan square y. Now tan y is x. We can call this equation 1 for our reference. So from equation 1 I can put, instead of tan y I can put x, so it is going to be 1 upon, therefore, okay, so similarly if you approach, you can also find out derivative of cot inverse of x. So similarly, by similar method, we can derive the derivatives of cot inverse of x would be, only minus would come there, nothing changed, 1 plus x square. By using similar procedure, you can easily show that, derivative of cot inverse of x is minus 1 over 1 plus x square. So we have also got derivative of tan inverse of x, that is 1 over 1 plus x square, and derivative of cot inverse of x, which is minus 1 over 1 plus x square. Similarly, we can go and we can also find out the derivatives of sec inverse x and cosec inverse x. So I am not deriving those. If you follow similar procedure, you will also be able to derive the value of the derivatives of secant inverse of x. So you will be getting something like 1 divided by x root of x square minus 1. Here the value of x must be more than 1. Similarly, if you do the cosec inverse of x, only you will get negative sign, remaining would be same, cosec inverse of x. So you shall be getting minus x square minus 1. Here also the mod of x has to be more than 1. Because if it is less than 1, then denominator will become indeterminate. Negative of square root does not exist, okay. So it should be more than 1. So we have completed almost the differentiation of standard functions by using first principle. So in our next lecture, we will try to apply these results what we got. So we will try to do some actual problems. So please go through these results and try to memorize these results, because now we will apply these results for the problems. Okay. Thank you very much.